All right, so I think I'm recording. I'm good to go. Here are the objectives. I'll let you go through those on your own. So just to review, we know at this point now that when we're looking at something that's radiolucent, we're looking at structures that are being radiographed that have a lack of density. So when we think about density, we're going to learn density in kind of a new term today. But what we've been thinking about with density is like the thickness sort of, or, you know, of the whatever the X-rays are going through. And it permits the X-ray photons to pass with little or no resistance and hit the sensor. And so an example of that is like your airspace, your PDL, your nerve chamber, things like that. Radiopaque structure is dense, so that it absorbs or resists the passage of the X-ray beam, examples being enamel, pulp, things like that, to different degrees. So we want to think about the ideal way our films should look. And you guys have seen a lot of pretty bad films because you've been looking at them on, you know, copies that I've been giving you. So you can see already how when you look at a nice, crisp, clear X-ray, it makes a heck of a lot of difference as opposed to looking at something that's like blurry and whitewashed and or too dark. So we want to see an image that provides a great deal of information, and especially since we want to catch things when they're small. The terms and the things we're going to think about is density in a different way. We're going to think density defined a little differently. Contrast, which is going to be one of the trickiest concepts, and then same size and shape of the object being exposed. We want to see as much of a realistic kind of duplication of the actual real item and then the picture of it. And then the sharpness and outline, nice outline. So when we think about density in this term, so we're talking about the density on the film, not the density of the person's like mouth or whatever. We're thinking about the overall blackness of the film, so the overall darkness of it. So the picture on your left is less dense than the picture on your right up here on the screen. The darker one is more dense. So visual characteristics of density. So primary factors that influence film density is going to be with your MA and your KVP, so like the power of the X-ray photon. So MA, the milliamperage per second, that is higher MA, turn up the power, you're going to have more density, a darker film. A lot of this is kind of intuitive. There's a couple times when you're going to lose that. You can't just rely on the intuition of it, of power up darker, because there's a couple of times when this is going to not work out especially when we're talking about contrast. But for density, higher power, darker image. So higher MAs, higher density, darker image, higher KVP, higher density, darker image. Exposure time, when you guys push the button on the thing when you come outside the room and you push from anterior premolars, bite wings, maxillary molars, mandibular molars, what you're changing is exposure time. So the molars are going to have more exposure time, a longer beat, more X-ray photons coming out of the head for a longer period of time than when you set it on anterior, shorter exposure time, less amount of time where the X-ray photons are coming out of the X-ray tube head. Does that make sense? You're changing the time. And so longer exposure, more X-ray photons, denser image. And you'll see that if you were to try it with Dexter just for fun, it's not going to be this super drastic difference like night and day, but it can be depending on who you have in your chair. But let's say you put Dexter there and you take an anterior PA and you set it on a molar. You're just going to see that it's darker, and then set it back to anterior and just compare, just so you can visually see that effect, because that'll maybe help kind of solidify it. Subject thickness, so larger subjects, thicker tissue, denser bone, less dense. And why is that? Why would it be lighter? Yeah, because they're just thicker bone, more bone, and it just gets more absorbed. The other thing that we think about that affects density is the source being the tungsten target. That's your source, because that's where the x-rays are coming, that's where the x-rays are being produced. So that's your source. So the tungsten target inside the vacuum tube, and the distance between that and your film. So the longer the distance, the lower the density, because it's that inverse square. When you go from here to here, you have so much intensity. When you double it, it gets weaker. Think of that concept. Remember the flashlight, and the light is the most intense and brightest closer to the source. And as you go out, it fans out and it becomes less dense. So that's where the source and your film, depending on how far and close or far away, it's going to be lower density the farther away it is. Too much density will make a darker film and conceal stuff. It'll hide the stuff you want to see. Too little density will just destroy detail. It'll just whitewash it all. And I just put this picture here because this is not actually highlighting what density per se, but it's an image to let you kind of see, like, here's your tungsten target, here's the film. So this is actually talking about magnification, which we will talk about later, and you'll actually see this in an activity in lab. You can actually see how this works. But I just wanted you to see that this is what we're talking about, the distance from the tungsten target to the film. So this is going to be less dense as opposed to your tungsten target being closer to the film. Now, that's not what this specifically is trying to highlight, but that's the concept for the density. So yeah, 8 inches, it would be more dense than 16 inches. And the reason is because of that inverse square law. So visual characteristics, so you can see here, the image on your right is dense, more dense, and you just can't see like the shape. So if there was some kind of incipient decay over here, I should just do my mouse so that everybody can see it. If there was some kind of incipient decay in here, you can see it here just great, but you come over here and it starts to hide stuff. You can't see, or take the canine even better. If something was happening on the canine, it's just totally obscured and it's too dark. You just can't see it. Secondary factors that influence density. So all those other things that we talked about were the primary factors. The secondary factors would be things that have to do with if you have a traditional film and you're developing it in an old-timey developer. If the development solution was either expired or too strong or too hot or too cold, it's going to affect it. So underdeveloped films are light, overdeveloped films are dark. If, again, with the film speed, the faster the speed, remember A, B, C, D, E, F, F is the fastest speed of film. So if all things being equal, your MA and your KVP are equal, and you use 2 different speeds of film, higher speed film will produce a higher density, so it'll be darker. Lower speed film will produce a less dense. That's not going to probably apply to you very often, if at all, because you're not going to use traditional nearly as often as you'll see. And any office I've ever worked in that used traditional films always bought like faster speed film. I never used slower speed, so it's kind of not super relevant to what you'll do, but it's important to know it, I suppose, maybe for boards or something. Okay, so contrast is the next one, and I got to grab my scarf. Yeah. Oh, like why it's faster? Like, I think it has everything to do with the emulsion, which we will talk a little bit about like the makeup, like the actual makeup of a traditional film in another class. But there's a chemical, they call it like an emulsion, and it's laid over this plastic film. And that emulsion reacts with the fixer and the developer. So I think what changes is that chemical kind of skin. It's like, because you can scratch the emulsion off before you take the x-ray, and then you damage the end result picture. That emulsion is necessary to make the picture. So I think what happens is they just have different, chemical makeups of it. And the old ones maybe needed more radiation. They might have been sensitive to light different. So the older ones just weren't as sensitive, and the newer ones, the faster ones, are more radiosensitive. So it takes less radiation to get a picture on the film. So I think that's the whole concept, but we don't really use traditional film anymore, so it doesn't really matter, but it is kind of nice to understand the process anyways. Okay, so film contrast, difference in density seen on the film. So when you look at a film, what you're seeing is all sorts of shades of gray, and you're interpreting pathology and normal anatomy through these shades of gray. So we know the basic, the darker is radiolucent, the whiter is radiopaque, and then there's just a variety of shades that we're reading the x-ray, and we learn to see what's normal and what's pathogenic based on what should be where. So when we look at this is, you guys haven't had any kind of Carey's interpretation yet, but when you look at this, can you see anything in this area that looks like maybe it shouldn't be there? You guys can see that. So once you train your eye to look at the break, the dark break in the enamel, it stands out quite easily. And some areas are harder to see, but if the density is not like a nice contrast, it gets really hard to see. So what you're looking for are shades of gray so that these areas, here's like some occlusal decay here. You can see that it's more shaded underneath the enamel in the dentin here. So there's some occlusal decay coming through the pits and fissures there. So we need that contrast in a film so that we can diagnose what we see. So there's two scales. There's the short contrast, the long scale and the short scale. And the contrast for the low contrast. So what you have to think about when you think about the variation between long and short is if it is low contrast, then what's happening is between every step of darker to darker to or we could start and say darker to lighter to lighter to lighter to lighter. It is a mini step between each, like you can think of it like a rung of the ladder, and each step you get progressively lighter or darker. So that is a low contrast, long scale, low contrast, long scale. We started out, if we start at the top, it's black, a little lighter, little lighter, little lighter, little lighter, and it's many steps on its way to white. So it's low contrast in between each step. And so it's a long scale because it's lots of little steps. Short, you can think of it in a very, very basic way. You can think of it as like black and white, short scale. I only got two options. Now that doesn't mean you don't have some gray. So I'm just trying to break it down into something that will trigger. If it's a short scale, I have few options, lots of black, lots of white, not a lot of gray. So something that will help you trigger it. So this scarf here would be an example of what? Long scale, low contrast, because there's lots of different shades. Well, there's really only, so many, but and it's a scarf, so it's really, really long. So hopefully that might kind of help it. And then if I meant to actually wear black and white, so that I was like, but I have black boots, and you can think of my pants as gray and my shirt is white. So I only have 3 things happening, and I'm pretty short. So you can think of, there's only so many options for short scale. You're going to go from black to white very quickly, and you're not going to have as many shades of gray. But if it's a long scale, you're going to have lots of, and you're thinking, that's not so hard, but wait till I put power in it. Wait till we add the power part. That's where it gets a little tricky. So low contrast images show many shades of gray between the black and the white scale, and we call it a long scale. High contrast images show very few shades of gray between the black and the white, and then we call that a short scale. So what are things that influence it? So what are the factors that influence it? So well, I don't know why it's talking about the loss of contrast. So if basically this is just saying here that if we don't have that contrast, we have sort of this generalized sort of whitewash. We don't have a lot of definition. The definition is gone. Under or over developing a film will reduce the contrast, decrease the number of gray shades that can be distinguished. So, so they're just highlighting here that it's the importance of proper developing, again, is important with traditional films, because if it's not developed properly, then you kind of get this either loss of all definition, or it's too dark and it conceals it. Okay. What happens when we turn up the power? Does turning up the power increase our contrast or decrease our contrast? So lower contrast, lots of shades of gray, and you're going to have a visual. And I actually have a little worksheet. I'm going to have you guys, after we talk this through, we're going to work on this. We'll do the worksheet all together. I'll do half on this side, half on that side, and just try and pass them around, because I'm still going to talk a little bit before we actually do this. Okay, so if we turn up the power, so we increase KVP, we're going to make it so that we have more shades of gray. And so that's going to be a long scale, low contrast. If we turn up or down the MA, we're not going to change contrast. So the good news is that you don't have to think about the MA. The MA is only going to affect what? Density. So MA only affects density. KVP, however, does affect contrast. When we turn up the KVP, we're going to have a long scale, lots of shades of gray, so it's going to be low contrast. But when you turn up the M, it's not going to affect contrast, but it will affect density. Okay, so here is an image. There's a couple things happening on this, and I kind of tried to duplicate it with this little activity. Does everybody have one? I feel like I have extras up here. Does everybody have? You guys have this in the back? You guys don't have it? So I tried to duplicate this so that we could actually work it out, and then you can make some notes on it. But it's not a perfect replication, because there's a few things that don't necessarily translate. But in this picture, so if we look over here, if we look at this upper left side, this is showing, so what we see here is these wavelengths. Remember, we were talking about the longer wavelengths, they're long and lazy, and the frequency is lower and they're weaker, right? So if we turn down the KVP, then these kind of weak powered X-ray protons, they will be able to get into these less dense areas, and they'll show up very dark. So anywhere, you know, that is less dense, these weak X-ray protons will be able to get in. But the minute the density of the material that we're trying to X-ray increases, it's going to stop them short, and then everything else is going to be white. So you're only going to get dark in your most like thin, less, you know, physically dense parts of the mouth. And then everything else that builds up kind of thickness and density is going to show up white. So you're just going to end up with black and white, or very little gray in between. So yeah, no, that's fine. So if you use low KVP, the power of the actual X-ray waves are going to be so that they will go through, they'll penetrate. So if you look at this thing here, they'll penetrate things like, you know, your airspace and your, you know, your periodontal ligaments and anything that's not dense, and it'll show up black. But then everything else that builds up in physical density, like your enamels and everything, is just going to be white with very little variation in gray to help you diagnose it, because it's just going to go, it's not powerful enough to get through it and give a diagnostic image on the other side. So you're just going to end up with like black and white. So this is saying long wavelength, short scale contrast, and this is basically saying like low KVP.
So if you're thinking low KVP on the enamel, it would be black or white?
It would be more white.
Okay.
It'd be more white. Now this is showing your long contrast. You've turned up the KVP. You can see the power of these X-ray photons. See how they are tighter, they're higher frequency, shorter wavelength. These are more powerful X-ray photons. They're going to penetrate. You've turned up the power now. They're going to penetrate things that are easy to penetrate, but they're also going to penetrate everything in between. So that's why you're going to get these nice shade of gray, is because they're getting through the easy stuff. They're getting through the medium density, and they're getting through the high density. But your weaker KVP is like burns out quickly. It's like, I can get through here, and then that's it. I can't get through anything more. So then you just end up with white on your X-ray, on your sensor, because the low power just can't penetrate whatever it is you're taking an X-ray of. So here's another image of it, and this is showing it in terms of more realistic grayscale. So 40 KVP is very low. So your 40 KVP, because remember, we're like 65 to 70 KVP in the room. So your low KVP has gone through this easy thin area. It's gone through this thick, little thicker, little thicker, little thicker, little thicker. It's all black. We get a tiny little bit of variation of gray here, and then it just goes to, white. And then it's just done. That's as much as it could give you. It couldn't give you any more information than that. Now 70, where we're at, this is ideal. Look at this nice variation of small changes up the ladder from dark to light. And that's because at every thickness, just the right amount is getting through to give you a nice diagnostic image. If the KVP gets turned up too high, the power gets even higher beyond what we would want it to. So 100 KVP, then it's just too dark all around. You don't even get hardly any light anywhere, because just tons and tons of all the X-ray photons practically are getting to your sensor. You see? Now this thing that's on the side that looks like stairs, what that's representing is something called a step wedge. And when they would actually X-ray this piece of metal. like a piece of metal that gets thinner and thinner as it goes down the steps. And so this is actually a real image of what happens when you X-ray this, whatever this is made of. I don't know what it's actually made of. Yeah. Yeah, so ours is 65 to 70, and that is kind of ideal because 670 has this really nice variation. You'd be able to see all the different little things like pathology, like, you know, apical, periapical, abscesses, in start of decay, because it gives you all of this range of gray at like 65 to 70. But if it's too low, you just get a ton of white that washes everything out, all your detail. And if it's too high, it's going to be dark and obscuring. So that's just with the contrast. So is what we're talking about. Even though it seems to overlay with contrast, with density, you know, but it functions differently with the heat. So yeah,
this is like going way back. But can you remind us? Okay, so KVP is the power when it pushes it to the other side.
Yeah, it accelerates the MA controls how many electrons are in your electron cloud, and the KVP pushes them, accelerates them to the tungsten target. And you guys don't ever change that. You know, you never change it on your machines typically. It's just set. So what you can do here, I seriously just hatched this little thing out of my brain. And so I don't even know how well this is going to turn out. But we're going to do it anyways. So what I wanted you to see here is, first I want you to write, if something is short contrast, what does that mean? If it's short contrast, is it what shades of gray? Am I hearing few shades of gray? Did I hear that? Black and white? Yeah. Short contrast equals few shades of gray. Is it GRA or E? Is it? I don't ever know. I should know. Long contrast would be what then? Many shades of gray. Many shades of gray. If you have dialed it up and you have high KVP, are you going to get a short contrast or a long contrast? I think it's high and low. Let's do this too. So here in parentheses, this is why we can just make all kinds of notes that we need. So short is also high contrast, and that's because there's a high contrast between black and white, right? That's where that term comes from. There's a big difference between black and white, but shades of gray melds it more together. So you have low contrast for long contrast, or low contrast equals many shades of gray. Are we all on the same page still? Wait.
Oh. Long scale.
Long scale, yeah. So you could even add this, because I missed the scale word, didn't I? So you can also add this. You can also put in parentheses scale. So long scale, short scale. I think that's probably what I meant to put. See, that's what happens when you hatch something out of your brain in like 10 minutes. Okay, so if we turn up the KVP, then what are we going to result with? Are we going to, is our end result going to be a long scale, low contrast, or a high, a short scale, high contrast? Long scale, low contrast. And if we turn the KVP down, we're going to end up with short scale, high contrast. So then what you can do here is you can kind of draw your picture. So what we know is up here, you can put low KVP. Will give you long, lazy waves, wavelengths. So you're going to have, if your KVP has long, lazy wavelengths, then as they penetrate down, they're going to get to, this one's going to make it all the way down. This one's going to make it all the way down. This one's going to make it all the way down. This one, not so much. And then this one, not so much. And then up here, if we have high KVP, we're going to have much tighter, short wavelengths, higher frequency, more powerful. And that one is going to result in, my wavelengths are not going to be very. That one's just going to penetrate more for more variation. And I just picked those not because I ended it just exactly perfectly, but just to demonstrate how it'll come through and hit the sensor. It'll penetrate through all these layers of whatever this is better. And then you can make any other little notes around there that help you. But I'm going to show you this next one that kind of shows the same thing. So again, another visual here. So here we have your high contrast, black and white, short scale, not a lot of variation. So you can think of short scale, there's few steps, few shades. And then that's going to result from your KVP being low. You can see there's just a lot of darker and a lot of light, but not so much in the middle. And then as we get a higher KVP, we get a low contrast, a long scale, lots of variations, many steps, many shades. So here's the little phrase to help you remember: long scale, low contrast, lots of shades of gray with high KVP. You gotta tell yourself a story about it. High KVP, long scale, low contrast, lots of shades of gray. Low KVP, SSS, like maybe find, so you got to like figure out a way to tell yourself like a little mental story about how it works out. Totally. Yeah. I mean, really, it's not like it's a hard concept. It's just that with so many like long, short, few, high, like it can get confusing, and I guarantee you it's on an exam. So you just have to like play with it and write it out. My best advice would be write it out until you test yourself. Write it out until over and over again until you have spit out the right story, or the right way that this works. I'm losing my words for that, but you know what I mean. And then, but this is a really good slide, how to remember the difference between high and low and how the KVP has affected it. I think that kind of sums it up nicely. All right, summary of where are we here? So we've been going for, another, let's take 5 minutes to just kind of shake that off and get a drink of water, and then we'll come back and we'll finish. It's 2 o'clock, so we'll come back at 2:05. So in summary, density is the overall blackness in this, when we're talking about the quality, density is the overall blackness of a film and can be changed by MA and KVP. And if your KVP and your MA are fixed and you can't do anything about it, but on ours, for example, you can change the exposure time, that can affect the density as well. So exposure time can also affect density. Contrast is only affected by your KVP. Okay, so some other features when we're looking at our film, some other things that we look at is sharpness, magnification, and then the image distortion, if the image is distorted or not. And there's some fun activities we'll do next week with a flashlight so that you can kind of see this. I mean, it doesn't work perfectly, but it gives you a really good, some of them work better than others, should I say. But when we're talking about sharpness, we're talking about reproducing a nice, distinct outline on the edge of the tooth. And you know how we always go in and we do the edge enhancer and it crisps up the edges? That lets you see things like, you know, incipient decay so much better. If it's overlapped, so much better. So we want to have kind of a nice crisp line, or as crisp as possible anyways. Magnification, equal enlargement of the radiographic image. So if something is kind of like over magnified, it might look kind of enlarged and blurry. You see that a lot with maxillary roots sometimes, especially like palatal roots. It just looks huge and blurry, you know? And so sometimes with distortion, we get that. We can get it other places, but that's just one place I can think of that seems to happen fairly often. And then image shape distortion, variation in the true size shape of the object being radiographed. So sometimes you'll get this curvature at the ends of the roots, just because of the way the film, you know, might have been parallel with the long axis of the tooth up into a certain point, and then just because of the way they sit in the jaw, all of a sudden they're not parallel anymore. So then you get distortion down closer to the apex. There's just not a lot you can do about that. Sometimes people also do have, you know, dilaceration in their roots, or they'll have things that happen, and so they are curved. But it can be from placement of the sensor as well. So image shape distortion. Penumbra is what we call that fuzzy margin, and you're going to get that on everything, has it to some degree. We just want to minimize it, but it's an unsharp margin surrounding the radiographic image. It's that, or like a blur around the edge. So that's the definition. It's important for you to know that phrase and the definition. That's a popular one for exams. So knowing that penumbra is the kind of fuzzy blur or unsharp margin surrounding the image. So image unsharpness can be minimized by keeping the film, so the sensor, as close as possible to the object, which is your tooth. So when the film and the tooth are close together, you're going to have a much sharper image. So that's great, but sometimes with the paralleling technique, we have to give a little distance. And so we have to put it back. Maybe we have to put the XCP and the bite block in the closer to like the midline. And so there's more space between the sensor and the tooth. We'd like it to be closer, but something's got to give. If you go for parallel, you might lose a little sharpness. If you go for closeness, you might end up with more foreshortening or elongation or some kind of other distortion. So it just kind of is the way it works out. But so image unsharpness can be minimized by keeping the film as close as possible to the object and by having the source of the film distance as long as possible. So we also learned that when the source is long from the film, then that can affect density. But we also want to, so by having the source as long as possible from the tooth, the actual tooth. So now we're talking about keeping the tungsten target farther away from the actual tooth will actually give you a more realistic sized image. So, and the reason for this, and this will help a lot when you actually play with the tooth and flashlight in lab. You'll actually be able to see this, and this concept will help. But when the target is farther away, you can see here, if it's farther away, you get this kind of spanning. Now, wait a minute, what are we looking at? Sometimes these pictures throw me, and I think I know what they're going for, and then yeah, it's just the magnification, and you can see. So source film distance, so source is your tungsten target, and your film, you want that distance as long as possible, but you want, oh, this is showing the tooth closer. That's what it's showing. So see, if the tooth is closer to the film, you get a more accurate representation. That's what they're showing here. So if the tooth is farther away, you're going to get a larger image. And if the tooth is closer to the actual film, you're going to get a more accurate interpretation of the actual size of the tooth. So you want to keep the object in the film. The tooth is the object. The film is your sensor. You want to keep those close together as possible, but then you want the source of your target and your film as far away as possible. And you can only get it so far because your BID is only so long. So it's sort of set up ideally. That doesn't mean that you're gonna, like, you want your X-ray tube way out here and then the BID stops because you're like, well, she said to keep it as long away as possible. So it's the distance between the tungsten target and the end of your BID is the good, that's the good distance. It's already built up that way. So you move that right in and snug it right into the ring, right? So you're not trying to keep your BID away from the patient's head. So 5 rules of image formation. So these are important to star this. This is, there's usually information on an exam from this slide. So X-ray should originate from as small a focal spot as possible. Your focal spot is the tungsten target. That's on the anode side, the little chip of tungsten, that's your focal spot. And for whatever reason, this is physics and stuff that's beyond my understanding, the smaller it is, the better. So you want the X-rays to originate from a smaller focal spot. Typically, it's only 0.5 to 1.2 millimeters. Once you guys start using your probe, if you haven't already, 1 millimeter is tiny. That's that's tiny. So 0.5 millimeter to 1.2 millimeters. The distance between the focal spot or the source, which is your tungsten target, and the object, which is your tooth that's being examined or that you're taking an X-ray of, that should be as long as practical, which, like I said, it's only so long. It's going to be as long as your head and then your BID, and it's not going to be any longer because you don't want to hang it out farther away from the patient's face. The film should be as close as possible to the object being radiographed or the tooth. So sensor and tooth as close as possible. The long axis of your tooth, the long axis of the tooth should be as parallel as possible. So that's going to affect where you can actually place the XCP. Because like I said, you want it to be real close, but you have this curvature of the palate and the patient, you're just going to have to find the sweet spot of where your patient can tolerate it, where it's parallel, and what have you. That's why sometimes we end up having to do X-rays with the bisecting technique, because you can get closer to the tooth, but you're not going to be parallel, right? So then you're going to end up having to bisect the angle and figure out what the right angle is to minimize your distortion. And then the last one, 5, the central ray should be perpendicular as possible to the film if you're in parallel. So if your tooth and your film are parallel, your central ray is perpendicular. So those are your 5 hard and fast rules for getting the best diagnostic, best replication of the image that you're trying to take the picture of. Okay, so in summary, image should not be too light or too dark with the density. The 5 basic tissues should be seen, and this is what we're, with a good contrast, we see the enamel, dentin, pulp, alveolar bone, and soft tissue. So those are your 5 basic tissues that you would expect to see if the contrast is set really nicely. The periodontal space, the lamina dura, and then the trabecula, the bone trabecula, that's will be seen with a sharpness. So when the outline of the tooth, that whole little kind of the lamina dura kind of going around the root, and then seeing that bone trabecula all throughout the bone, that's going to be some nice sharpness. The buccal and lingual cusps, tips, they should be superimposed. So I don't think we're going to have time to do it, and the Friday group still needs to do their critique. But next week, I'm going to start out class by, we're going to critique an FMX together, and we're going to talk about some of these things that I think just we haven't. There's a video, and I know I say watch the video, and then maybe 10 people watch the video, and so we're gonna hit it a little harder, and then review the criteria for retaking, because I kind of explained it a little bit for the Monday and Wednesday groups while you guys were doing your critique, but I think we need to just really zoom in on it and hit it a little harder. But your buccal and lingual cusps should be superimposed. And if they're not and they're tilted and you can see a little bit more of the occlusal surface, that's distortion. There's distortion, because if we come in parallel, the buccal and lingual cusps should be superimposed on each other. Maybe you see a little bit, because everyone's teeth are different, but so maybe there's a slight, maybe you can see slightly the buccal a little more than the lingual or something, or it's hanging over, but typically they're superimposed. So we have to think about that. And then all needed structures of an accurate diagnosis can be seen. So coverage, we just have to make sure that we're seeing all the stuff that we want to see. Okay, so here is, what are we showing here? So for just looking at different. Well, obviously this is showing the on a ligament space. Buccal and lingual cusps are not superimposed. Well, I think this is wrong, because this is pointing to the root. It should really be pointing to here. So what do you see here and here on these premolars? I think this might have gotten, this slide the animation might have messed it up, but yeah, you can see. So here we can see the difference between the buccal and the lingual cusps are quite severe. Now up here, I think that's all it was probably trying to point to. So up here, you can see that the buccal cusp comes out a little bit lower, and that's not unusual, or a little bit higher if we're on the mandible. But look at the vast difference, especially on this one. This one probably might even be somewhere in the range of slightly normal with just a little distortion, but this one is pretty distorted, right? Yeah. Yeah, this one has some this one does have some vertical angulation on it. It's hard because you can have vertical angulation on a couple teeth in a picture, but not all of them. So when I'm grading the vertical angulation, I kind of grade up a little bit easy, because if every single one has vertical angulation, I'm like, well, that, and the roots look really short and you see a ton of occlusal surface, then I'm like, well, that's more obvious. But like something like this, you might go, well, these teeth look okay. Those aren't, the cusps are pretty close together, but this one has quite a fair amount of distortion, but it's also at a different angle. But yeah, so that's what this is trying to point out, the difference between this, the way this image looks, and then the way these look up here. Okay, so I just put a few more of these in here to talk a little bit about the foreshortened and elongated images. So does this one look like there's some distortion happening in this image? And if so, what makes you think it looks distorted? Yeah, the roots definitely are kind of obscured. They're kind of all kind of washed out. There's some of the contrast there, right, is not very good. Yeah, Liddy? Yeah, this is you can see some sinus. This is actually the zygomatic process, which we'll talk about more later. And sometimes it looks a lot like the sinus, but there's some key differences that you guys will be able to pick out, no problem. But yeah, that some of this is just obscuring it. But the angle of what it is, one of the biggest things that you can again look at how the lingual cusps end up here, and then the buccal cusps look all dragged and stretched down. So look at the space here between where the cusps end here, and how they get dragged down over here. And they just kind of have this sort of like the cusps kind of have a dragged out look, and then the roots end up looking kind of distorted and usually kind of short. So what about this image? Does this image look like there's foreshortening or elongation? It's probably closer to, I mean, yes, they look long compared to this, right? But they're actually probably fairly okay. There's, some people just have long roots. I mean, that's just a thing too. There could be a slight bit of elongation there, but for me, I think it's closer to normal. What about this one up here? Yeah, so again, look at the crowns here and see how you can see the occlusal surface. So there's a little bit of foreshortening. And so you might say, well, this looks okay. Like those are pretty long roots. But if you compare them to something that was taken like really straight on, these roots do tend to look much longer, and maybe these are shortened. This one even more so, and then this one probably even more. Now this does have a shorter root in general, just because it's a wisdom tooth. So there is some of that, like this root ends here, but you can just see that there's more occlusal. That's like, to me, that's the big key, is there's a little bit more occlusal surface showing. So it wasn't taken straight on, like perpendicular. And then this one, this is an occlusal image taken on a kid, because you can see their permanent central incisors up here that are starting to come down. But does this look like it's foreshortened or elongated? Yeah, they just look stretched, right? So I feel like it's just something where you just see it and they just start to have this stretched appearance, or they have a smushed appearance. And then the ones that are like a little distorted, it's, as long as it's diagnostic in real life, nobody's going to get really that worked up about it. And it's a little harder to identify. So I tend not to be too hard on that. But that is stuff you should look for. Is you should look for seeing more of the occlusal surface and kind of a stunted root, or just kind of like this stretched out appearance, kind of just looks kind of long. And sometimes things will get distorted. Like look at the crown of the tooth. Like look at the incisal edges, because like all of this looks pretty realistic to what I would expect a tooth to look like. But these all look kind of stretched, like the crown, the whole crown portion and incisal edge, it all just kind of looks long and stretched out. What about this up here? Like, that's kind of like, I mean, like that's obvious, right? You're like, that looks very stretched out. The roots even go off the edge. It's just totally stretched. So that sticks out a lot more. Something like this, does this look foreshortened or elongated? And that's a little more obvious too, right? Like everything just looks blunted, and it just seems like the angle, instead of coming at the facial surface, it's almost like it came underneath a little bit and was looking more like directly on the incisal edge, as opposed to, coming more perpendicular to the teeth. So here, these look a little stretched out to me as well. And then this one also, you can see just more occlusal surface and things look short. Now, I think their roots are short anyways. So I think there's two things happening, but they definitely did foreshorten it though. There is some foreshortening here. Okay, so now we are gonna look at, I had turned, oh, I didn't. Let's see, what do we have left? 25 minutes? Just don't want to go over. Okay. So analysis of errors and artifacts. This is mostly having to do with traditional films. So a lot of this is not going to be stuff that's going to be very relevant with with our digital films, but in lab, we'll have a little practice looking at some real traditional films that have some errors, and then you just have to like figure out what that error is. I was asking people that taught radiology and other programs, and a lot of them said that on a national board, like a 9-hour national board, you might have 1 or 2 questions about traditional x-rays. So, you still want to know it for the material that you're going to be tested on in this class, of course. And then, but overall, it's probably very low stakes. It's not like there's going to be a lot of traditional film questioning on the national board, but it's still, we still have to include it. So we still have to test on it and grade it and such until they until they stop testing on it completely, which would probably happen at some point, I imagine. So there's technique errors and there's processing errors. So the technique errors are what we've already talked about with closing contacts and elongation and foreshortening and all the things involved with actually taking it. And then processing would be once you actually have to put it in the processor and develop. So the techniques are, like we said, placement, horizontal angulation, vertical angulation, and beam centering. If the patient moves, so that's another reason why we have that little window when we put the XEP in a patient's mouth, and especially if they're gagging or that hurts or something like that, when we run out, we can look in the window and push the button and see if our patient spit it out too fast or, whatever, moved when they gagged and moved or something. So we can see if that error has happened and figure out why something didn't turn out. But you can see if the patient moves, see how it just looks blurry, like you can see like double of the fillings here. It's like a double image sort of. You can see that the patient moved during this image. If the film is backwards, so who knows what happens if you put our digital sensor backwards? Nothing, right? So in this one, this shows like a little chip. That doesn't happen with ours. It just, nothing comes up. It's like, why isn't my picture coming up? And that's just when we put our sensor backwards. If you're using traditional film like this, you'll see the lead foil. So we'll take, in lab, we'll take apart some traditional films and you can look at them, see what's inside. I think I already did that for one group just because we were talking about it for a second, but there's a lead foil in there. And if you put it backwards, then that will overlay over your image. The dot artifact, so when we were mounting our films and you have a little bump, the dot artifact, if you put that in, if you don't put the dot in the slot, which is the slot holds the traditional film, if you turn it upside down and the dot is going superior, it's likely going to be around the apices of the roots, and then it could look like a periapical abscess or something like that. So the term dot goes in the slot to always keep that dot artifact along the occlusal surface. So that would be an error is if they hadn't put it in there in the proper holder orientation in the holder. Dimensional distortion. So this probably has to do with they bent this film and maybe the whole film was just like, maybe they had really bad tori or something, the bone that can grow down on the inside of your mandible. Maybe they had really bad tori, and so maybe it was flexing kind of up over that. And they also, you can see with this crease that they bent it. So it just kind of made this whole sort of elongated, blurry look. Bend marks, again, this is just super common. I used to bend my films too, because again, the corners were pokey and patients complained. And so you would bend the corners a little bit to make it more comfortable for your patient. So that's what these are. You would try to do it minimally so that you wouldn't, you could still get these diagnostic images, but that's what this would look like. This is a lot of bending. And then this is like fingernails. Like, so when somebody was handling it, they maybe had long nails and were just poking at the film or something. I don't know quite how you would get that many fingernail marks on a film, but somebody did. So that just basically like pushing or scratching at it will affect the end result. a double image. So you take a film and then you put it in a cup, and then, or this was, so we always had a routine before. So you'd have your cup of unexposed and then your cup of exposed, and you'd take the film and then you'd put it in your exposed cup. But if somebody didn't have a nice process that helped them keep them straight, they might grab the same film and take 2 x-rays on the same film. So you can see they took a lower anterior and a molar PA on the same film. So so you got your anterior teeth here, and then you have your molars there. Kind of funny. So a double image. And then some of you might have seen this already. What's this? The cord. So that happens quite often. So we just have different films. It's harder to do sometimes when you're taking verticals or, just certain ones. And we always want the cord to come out the front, going alongside the rod or whatever metal bar is, and try and kind of have it out to the side, and it doesn't show up in your x-rays as often. And I feel like I skipped one, did I not? Nope, it's not. And then if a film is blank, so blank, no image, doesn't often happen with digital, but if you forget to align the BID or you forget to turn your machine on. But what can happen is a lot of times somebody could take a film and they got everything all lined up perfectly, and they take the film and you only see a tiny little bit, and 3/4 of it is white. So what happened there? It cone cut, but why did it cone cut so much? If you got the BID snugged into all 4 corners and you go and you take your picture, yes, the ring doesn't get flipped. So sometimes especially when we're moving from the upper left, lower right to the other side, we move the bite block, but we forget to flip the ring. So then it's why did it do that? So what error do you think this is? Let's see if someone can figure it out. Bite block? No, but that's a good guess. It could be. What kind of teeth? Dentures. Someone left the dentures in the patient's mouth. Isn't that funny? They're ghost teeth. So this is somebody, they left the person's likely full upper denture in their mouth.
Would you want to do that so that way, or no, because you want to see the gum line too?
Well, it's kind of funny because honestly, if you usually would take a PA, so you might leave the denture in there and so the patient has something to bite against. I always took out the patient's denture but sometimes it's really hard for them to hold the XCP. So I have had times when I've had them put their denture back in, but it's hard for them to bite hard enough. So you still end up sometimes with not getting it seated low enough to get the apices. So a lot of times what we'll do is we'll put a bunch cotton rolls or something to try and get it so that it seats. But that might have been what they were trying to do here, is give them something to bite against. And that might have been why they left the denture in, or maybe it's just a mistake. I don't know. Kind of funny. Okay, so these are what the developers look like, and they're still out there. There's another one this one is really common, and this would be without in a dark room, and this is if there's no dark room, that this little box is the dark room basically. So it could be out on a counter. It's very unlikely that it's probably very few and far between offices that still go this route, but it's possible that you could find it somewhere. But basically the films slide in here. And there's these little kind of rivets that you put one film in, one, and then you start over again. And it usually a light says a ready light, so that you put in your film and then it's ready. Now you can put in the next one, and you just move down the line so that you don't overlap films, because that's a common error, is that you'd overlap the film and then they spit out up here. So if you're in a dark room, you don't need this, but if it's out on the counter outside, then you need a dark space to put your arms inside of here and take the film apart. And they just run through rollers through fixer and water and developer and water and dry off, and then they come out the other side. So processing errors, so higher density film, the causes, if the film comes out dark and it's has a higher density, then it could be that too much time in the developer temperature is high, it's too hot, too warm, inaccurate thermometer, that again, be the temperature, and then overactive developer solution. So maybe it's too potent, they didn't, like if they diluted or whatever, it came into kind of too potent and it just got overdeveloped. Low density causes could be just not spending enough time in the developer. The temperature is too low, so it's too cold, and then the developer solution is old. They have to change it, like, I don't remember, once a week or once a month, or they have to change it a certain amount of time. And if they don't stay on that, they have to clean it. The rollers can get dirty. It's like, ugh, everyone always hated it when it was that time to deal with the processor. And the chemicals are kind of nasty too. They're kind of stinky. So it's nice that that's really not a thing anymore, frankly, but those are issues. If it came out too light, then the temperature is probably too low, or the chemicals are probably not, they're probably spent, they're just depleted. This is the tricky part that takes a little bit of getting it straight in your head. So if there's dark spots on a film, on a traditional film, there's some dark spots. Those are chemical spots from the developer. So dark spots are a developer spots. Sort of. This is saliva contamination. Again, it's just kind of dirty looking. It just means that it got wet and some of the emulsion got messed up before they took the x-ray. And then the fixer cutoff means that no fixer on the black area, it only got developed. So nothing got fixed, basically. It only got developed. So it's hard to even really give you guys an activity to help you remember this. And I doubt that there's going to be very much to be tested on. But just remember, if it's a fixer cutoff, it didn't ever get fixed on this portion of the film. So say the fixer solution was low and that part of it got missed and it only got developed on that side. So it came out black. So then you're going to have the opposite. If it's white, you're going to have the opposite. So we'll see that in a second. So black artifacts. So here is overlapped film. You can kind of see the film, like almost an impression of another film. So they stuck together during the development stage. This is fingerprints. You can kind of see that. That's kind of obvious, little fingerprints all over. And then this light leak is kind of obvious to see how it almost looks blurry. It's not a sharp black line. This is the difference here. See how this is more sharp? There's not so much of like a fading, whereas this one, it kind of has this fuzzy look all through here. So the door, like maybe someone opened the door while they were sticking this film into the processor, and that little tail end got hit with light before it went through the developer. So white artifacts, so developer cut off. So it didn't get any develop, it only got fixed on this part that was white. So here, and then here's some fixers spots. So fixers are white. Air bubbles through here. You can see some air bubbles through there. I don't even know how that. Brown. So this is a good one to remember. So brown would be exhausted developer or fixer, or insufficient fixing time, or insufficient rinsing is probably a big one for it. The chemicals didn't get rinsed off very well. So that you might want to start. Static electricity, that's kind of self-explanatory. It kind of looks like lightning. Moisture contamination, again, that's saliva. You kind of can just see some of these dark spots that showed that earlier. Little bubbly kind of looking. And then film fog. So this can be from like an old film. Maybe they're using film that have been around, or maybe they didn't keep them in a safe enough place. So they kept them in a drawer that got like a minute amount of radiation. And so it just made the films not as effective when you actually went to use them. So just different things, or it could have something to do with the high temperature in the solution. So different things, but if it's kind of foggy, improper film storage or outdated films would be a big one. This is a torn emulsion. The actual like chemical coating is torn, so it's going to make these kind of ripped looks. So what is this one here? What do you guys see on this one? Exactly. What about this one here? I think it looks light leak too. Yes, I think so too, because it looks a little fuzzy, huh? It's a light leak. Tips for feeding your films. So I kind of talked through it already, but films should be fed into the machine slowly and straight on. And if the film is bent, the unbent side should be inserted first. So, oh my gosh, you guys are gonna be like, when am I ever gonna do this? When am I ever gonna insert a bent film into a processor? Don't feed damp films into the processor. They should be perfectly dry. When you're taking them apart, your hands shouldn't be wet. Films should not be fed too quickly or in too fast a succession. Those old machines would give you like a ready go light, like, okay, next one, okay, next one. So you just had to wait for the light. The end. 8 minutes early. Have a good rest of your day. Thank you.